now we're using a similar relationships of everything we've derived, except instead of using the linear position of x, we're going to use an angular position, theta. And so all of these equations that we derive, you've got the energy equation here, is very similar to the energy equation that we had derived previously, except that we have this angle. So the inductance is varying with an angular position. We derived this from from all this calculus stuff that we touched on. The co-energy, which is an easier thing to work with, right here, same expression, 1/2 Li squared, but the L has an angular position dependency. In general, you can derive the torque the same way we derived the force from, as you recall, when we did the force, we did a partial derivative with respect to x. Now we're doing a partial derivative with respect to theta. And the energy has a angular dependency. There's this negative sign that comes out of the expression if you use energy. The other important point is that we are evaluating torque at a specific instantaneous value of flux. If we use co-energy, we use this expression here. There's no negative sign. It's the partial derivative of co-energy, and then it's evaluated at a specific value of current. And either of these expressions will simplify to this very key expression here. So really the next exam, for example, if we want to think about, what is it you need to know, is that we're going to apply, I'm going to give you some examples of how we apply these equations. And consider a magnetic structure, a core material, this gap that we cut out of this material here. And that gap can move in an x direction. So we wind up with an equation for the inductance that was equal to mu naught. Oh, I didn't add in the turns. Here's our copper wire, and we're going to apply a current to this system, and it has n turns. And we're also going to assume that the mu relative in this is approaching infinite. Since we're doing this, we're actually going to end up with a pretty linear problem. We're going to be able to simplify our result to something that you've probably seen. So the expression for this inductance is n squared. We have now a variable gap area with x. There are two gaps, right? There's a gap here and there's a gap here. We're using g to represent that gap distance. So this would be over 2 times g, where the area of the gap, and in this case we're going to neglect fringing. It's the length of the stack times the dimension d, which we're going to say is this dimension right here. We're going to say this is the length here. L times d, 1 minus x over d. That would tell us that if x equals 0, which means you're in the 0 position right here, area of the gap at 0 is L times d. And if x is equal to any x, I'll just call it x naught, any x position, ag of x is equal to 1 minus x position over d times L times d. If x equals d, ag of x is equal to 1 minus d over d, L times d, so it's equal to 0. So the gap's varying between this value here and 0. So I'm going to take my energy expression and say that the energy is equal, we know is equal to the lambda x squared over 2 Lx. Now what I can do at this point is I can say, okay, well, I don't know what this is, so what am I going to do here? Well, let's go back to what we knew before. Because we have a linear system, y equals mx plus b, there aren't any cosines or sines or logarithms or e to the x's or anything like that. Essentially, what is a linear system? A linear system looks like a straight line. So if I were going to say this is lambda and that's x, well, I have a linear relationship between lambda and x. So because of that, we can say that lambda x equals L of x times I. And now we can plug in f into this force expression. We can actually make it a function. I'm going to leave it on this left-hand side as lambda. But on the right-hand side of the expression, I've got now on the top L sub x I x squared over 2 times L x. And now if I simplify that, what made this linear? So we can ask that question. Number one, the current that we put into this, I'm going to say is equal to some constant current, I naught. So the corollary to this was if I is a function of x, and it's changing with x, then the system is not linear. For example, what if I of x, so we were saying up here, I'm going to make it really clear, I of x is equal to the same value everywhere. But if we said I of x is equal to some, and let me put this as a capital value here too. If we said it's inversely proportional to x, it's no longer linear. And we can't use this. And there's a very complicated example that the text goes through to show that. We're not going to take the time to do it in class if you're interested. But once we do the rest of the problem, we find the force. And you can go through this thing and prove it. You would have to go back and use this expression. So this is the general expression. So this is for all cases, linear and nonlinear. And I'm going to give you a little bit of a hint. Here's a linear, here's a nonlinear system. So there's your nonlinear system. That's just an example. Another one is too, if L, which is, you already know this, we've been through this with our chapter 2, L sub x, you have L, let me put it this way, L also changes with I. So if your L changes with I, an example of that would be saturation, right? Or a saturated core. In which case, remember you have your B and you've got your H. with a core. Let's do our BH curve. Here's the linear region. So everything we could use in this region, we could use 1/2 Li squared. But once we get into this region here, we would have to use the general expression to find our energy. And if you remember that this B, as we went through Faraday's law, is proportional to lambda. And H is proportional to a current. So we could rewrite, and we're going to start thinking about these BH curves like this. A lambda I curve. So I could write the same thing here like this. Let's have a lambda I curve. And we're going to come back to this in a moment and introduce a very important principle. But really going to be thinking about magnetic systems in terms of lambda I for a while, not BH. Is that any questions about that? Okay, so what about force? Because that's what we're really after. We're actually trying to talk about motors in this class. So if we had a linear motor, and this is a mechanically linear motor, or actuator, as they're typically called, produces a force in one direction with power input. So we're going to take a derivative now, and we're going to say the derivative of energy is equal to the partial derivative of the energy. There's really two things that make my energy change. Partial derivative of the energy with respect to position evaluated at a specific value of flux linkage, times the dx, plus the partial derivative of the energy with respect to lambda evaluated at a specific position x naught times, I think I have to put a squiggly here, okay, so there we have it. Now we can compare this expression to our other differential equation that we showed you, that we solved by integral. And it looks like this. Okay. So what we can do from this is we can say, well, we're really trying to find force, and this expression here, right here, this expression looks like this. I mean, on the left-hand side and the right-hand, it's the same, but the right-hand sides are different, so there must be a correlation. So we have a d lambda here, and we have a d lambda here, and we have a dx here, and we have a dx here. So really what we're after is we're after the force. So we're going to find the thing that correlates to this coefficient. So this is a coefficient right here. And that would be equal to negative f sub FLD. So the general expression for force is F due to the field equal to the negative partial derivative of the energy with respect to x evaluated at a constant or a specific point of flux. So this is your general expression right here, which I'm going to emphasize. So if someone was to give you an expression for the force as a function of x, if you take the derivative of that, you would evaluate it at a specific flux. You would get the force. We also know that we found an expression, a general expression for energy, which was equal to this. So we could also plug this expression into that. Now what we would do is we would basically, here, let me make it a little clearer. Let's plug the energy as a function of x at a specific lambda naught. So that's lambda naught squared over 2 Lx. We're going to plug that into here and take the derivative. And so the force as a function of x ends up being equal to this, to negative of the partial derivative with respect to x of lambda naught squared over 2 times Lx. That's the same as saying take the derivative of lambda naught squared over 2 times L of x to the negative 1 power. Just to kind of spell this all out, right? So the basic derivative ends up being this. This lambda naught squared over 2 comes out, and you end up with the derivative. This is a general expression of the inductance with respect to x. So there's your second general expression that you can use. You can use
Quick question.
this or the other. Yeah.
Why does the negative drop off?
Because of doing the derivative, right?
Okay,
So you do the
thank you.
derivative, you're going to get
Oh, that's right.
negative 1 times the derivative of Lx dx.
Oh yeah,
That's
that's
all
right.
it
Thank
is.
you.
Yep. And it's a general expression, right? So if you if you want to if you have x, if you have L sub x, use this. If you have the energy, use this. So you could actually always come back to this one here, but then you would have to calculate the energy. If you already had Lx, you could save yourself a page of work. So if we go back to our plunger example, we have an L of x in that plunger example, right? If we go back up to that example, it was this expression right here. So let's just use that, take the derivative of that, and we can find the force. So there you go there. So the derivative of that x is equal to remember, mu naught n squared LD 1 minus x over d 2 times g. So this is all a constant right here. We'll just call this k. So we have, trying to take the derivative of this whole thing. And so that would be negative k over d. That would be the dl. That's the derivative right there. And then if we wanted to find the force, it would be the lambda evaluated at a specific position, because we'll have a different force at different positions of the plunger. The force will be varying. And so we would say that this is L, some position of x times the current that we had, divided by 2. So this would be the force at a specific x and a specific lambda. So all we would really need to do is plug in this function here that we had for L. So that would have been mu naught n squared LD 1 minus x over d, but we're at some position over 2g. times negative k over d. So there's our force. Again, the thing what you're doing is you're evaluating the force at specific, these are specific points. I want to give you an example, and this is a very simple, what I would call a reluctance motor. And one point I want to make about all of these examples that we're making is that we like to think about motors, as rotating continuously. And that's a tricky thing to do, actually. And so all of these examples, we're really writing them in terms of scalar current values. So it's really like an instantaneous value of current that we're evaluating it at. So that would be like this current right here. In some cases, there may be a position dependency within the current. But ultimately, and this is just a precursor to where we're going, ultimately, these currents are going to be AC currents in one way or another. And in fact, every rotating machine ends up with AC armature currents. And I want to go back to that at the end, and we'll talk about armatures and fields. But let's just get through this example. So what we have is, it's a motor. If this was what I'm trying to say is that if this was going to have a continuous rotation, where you've got an angular rotation theta, and it keeps moving, you'd have to play some tricks to make that work, and you'd have to have an AC alternating current coming into this coil. And I'm not even sure if that would work. It would probably just go back and forth and back and forth. It wouldn't rotate in one direction. So it'd probably just go one way, the other way, one way, the other way. We don't really have a true rotating machine yet. But so what we're really focusing on is just generating a torque which will move this thing, which can move in a rotational direction. Now what we really have here is just like a typical magnetic component. We've got a winding around it, and we've got a core. That's what this whole thing right here is, an iron core. We're going to assume that the iron core has an infinite permeability. Now this particular problem I'm showing you is almost identical to a homework problem. And it is example 3.6, I believe, in the textbook. So if you're having trouble with this problem, go look at that example and review this lecture. It's a little bit different, but the reason why than many of the other problems that we're showing, and the reason I'm doing this is to really tie it back to the magnetic circuit. Now what we have, because we have a coil that's exciting this core, we're going to create a flux in the core, and the flux is crossing a gap. So you can imagine that the flux lines are coming out, and they're going to try to cross this gap into the moving part of this thing. And then they're going to try and cross the gap here. And so what you see is, in this position, there's just a portion of the gap that the flux is crossing. And everything that's outside, like this portion of it right here, there's no flux other than leakage flux that's going through it. And if you were to move this thing to, say, a 90 degrees angle, like along that angle there, it would have no flux at all going through it. So since we have a flux, and we've got a coil, we've got a a core, we can also apply Ampere's law, and we can find we have an infinite permeability inside of the core. So the only place where we're really going to have any reluctance that's non-zero is going to be in the gap. And we are then therefore only really concerned about the air gap magnetic field intensity. And so if you were to apply Ampere's law to this circuit, you could find the H in the air gap, and it would simply be equal to the number of turns times the current divided by the total gap. So you're going across the gap twice, 2G. So this is really coming from H dot dl equals I, right? Or Ni. And we don't have to find the reluctance of the core because of the infinite. We just find the reluctance of the gap. So it's quite simple. Now what I'm going to introduce here is just a different way of looking at the energy, or the co-energy in this case. Because, so first of all, if I look at this problem, you say, well, what have I been given to work with, to start with? There's a current. So I know that this is going to end up being a co-energy problem. Second thing is, remember that I told you that current is proportional to H. And that's clearly the case if we look at this expression here, right? Because the N is a constant, the gap is a constant, and really that's what Ampere's law tells you. Also, B, and I don't know if this is going to be that important because we're not doing this with energy, we're doing it with co-energy, but there's a more difficult problem where we demonstrate this, but I'm not even going to go into it because of time. But B, or flux, is proportional to B. So if I have a problem where I've been given current, I know I'm going to use co-energy. If I have a problem where I'm given flux, I know I'm going to use energy. And you've learned everything so far as what we've been doing in this chapter in terms of lambda and I, but we could easily instead go down the B and the H path, and that's what this is showing. And so what we can come up with is we can come up with an expression for the co-energy of this system. And that expression is simply this. The co-energy will be equal to the integral over the volume of mu naught, everything that's happening is only happening in the gap, times the square of the magnetic field intensity divided by 2. We're going to integrate that. Now what we're saying here is that this expression here, mu naught h ag squared over 2, has a duality or a correlation to 1/2 Li squared. That's really what this expression is saying. And to work out the homework problem, you would have to know this. And so that's what I'm introducing.
Mr.
Right
Kasna,
now. Yeah.
Before you go further, can you tell me what's the subscript beside the H, the first H just below the graph? Is AG? Or
Yeah,
what is
AG.
that?
Yeah, AG.
What's
Air
AG?
gap. Air gap.
Air gap, okay.
I'm matching the homework problem. AG. So it's, and so anyway, we're really introducing this other way of looking at co-energy right here. All the rest is simply geometry. And here again, the homework problem can help you. I mean, we're not really trying to test your geometric skills, but how do you come up with what's the volume that we're interested in? It's really the volume that I showed right here, what's happening in the gap. So if you were to imagine this little, that's like the cross-sectional area is here, right? And then this is the width of the gap there. So we're really talking about what's the volume that the flux is occupying in the air gap, the total volume. That's what this is about here. And it's going to change because this thing is allowed to move. And so the expression, I won't go into how you get this, and if I encourage you to look at the example. This is just because of time, but go look at the example in the textbook. I'm using a little bit different symbols than the textbook has, but what I have is the length of everything that's in the gap is L. So I have L, that's part of my volume. I've got the gap, that's another part, that's a constant. The only thing that's moving is this part of it here that I circled here. That's where you have to do a little bit of geometry. But the expression ends up being R. We've defined R as the distance from the center to the corner of that moving piece, plus we have to take into account the width of the moving piece, which corresponds to the width of the entire magnetic core. So that was A. And, no, I take it back. Where is the A at? Well, I don't think I need to worry about the A. I apologize. Can't read my writing. It's just, this is the expression, 0.5 times G, the gap length, times theta. So this whole expression right here is the theta dependency, and it's really what you're always looking for. Now, since we have two gaps, there's a factor of 2 times this whole expression here. And there is your energy. So now you just have a co-energy expression. And so if you were to just multiply everything out for the co-energy, you end up with, and we're going to take this expression here, HAG, and plug it in here. So that means that we'll end up with the turns and the current and everything else. And so it ends up simplifying to this expression here, mu naught n squared I squared times the length times the radius that we defined plus 0.5 G times theta. And this is the thing that will vary. And then that's divided by 4G. And so if we want to find the torque, we would simply take the partial derivative with respect to theta of this expression, which is quite simple. Just take the derivative of it. And so the torque, and we're just using this equation right here. So the torque ends up being equal to the partial derivative of that co-energy in the air gap with respect to theta. And we're also going to evaluate it at I. What that means is really this. I is not changing with theta, okay? We're evaluating at an instant point. And that's a very key thing to remember. So this is I. It's evaluated at a current I. And so your final expression is mu naught n squared I squared L R plus 0.5 G over 4G. So this would be your final answer. And I think the homework problem is identical to this. I want to point something out. Notice that we didn't calculate an inductance, did we? Could we have done it? Because we could have used this expression instead. It wouldn't have been difficult to do this, but it would have taken time, and it wouldn't have been necessary. Because if if you've got any, you already know with a structure like this how to calculate the inductance. So what you've got is you have a position-dependent inductance or a spatially dependent inductance. And you could have derived it, but it would have taken extra steps, and it wouldn't have been necessary. And that's the key point of this example. I'm going to give you another example where you actually would use inductance. And this is, I'll call this a single-phase reluctance motor. It's actually very similar. It's looking more like some of the actual rotating machines, motors or generators that we're going to talk about. And what that means is it has a shaft, it's cylindrical, it has only one winding. There's actually two pieces to this, and I think maybe now's a good time to introduce it, that you're going to have with any machine, rotating machine. You have a stationary part. This is called a stator, and that part is usually fixed, right? It's usually on some kind of a mount of some kind that's holding everything in place. And then you have this part of it that you're letting it move. That's called a rotor. Now these are the general terms for these things. Some people are used to hearing words like armature and things like that. Those terms are really artifacts of specific machine implementations. And a rotor is not an armature. You might have an armature that is on the rotor. And I just want to make that very clear to everybody. So the general term is rotor and stator. I've got a winding that is right here. And notice this winding is going down the axis of the machine. So you're just going down this length of the machine. And as a result, it goes into the machine, let's say on the top. So if I were to kind of zoom in on this thing here, there'd probably be a little X right there. And there'd be a dot right here. And in reality, what's happening is on the other end of the machine, you've probably got this winding folding over around the outside, an end. They usually call this like an end winding. So it's going to come back to the other side. And as a result of this, you will have a flux that's produced that if you just apply the right-hand rule and assume that your hand is going in, you're in where the X is, and the flux is in the middle. So there's a flux that's being produced as a result of this winding in this direction. So a lot of times you just see an arrow that says, okay, I've got this flux right here in the quadrature axis to the, when I say quadrature, to the line between the supply and return of this. That's where your flux is, right here. So anyway, in this example though, because you have a winding, you can have a flux, you can have a flux linking that winding, you have an inductance. Remember our general expression for inductance was turns squared. This is a self-inductance. So if you only have one winding, you've only got a self-inductance. Turns squared divided by the reluctance, whatever the total reluctance of the machine is. I'm going to introduce a new term which I call permeance right now. Permeance is the inverse of the reluctance. And so I can have an inductance that is N squared times the permeance. So these are equivalent expressions. It's easier to think about rotating machines in terms of permeance instead of reluctance, because what we're really after is we're after an inductance that's going to vary with rotational position. So that means that I've got, starting at the center of this thing right here, I can create an axis, kind of an x-axis, if you will, and there's an angular movement, theta, of this thing. So it's moving in this direction. And what is happening, though, is that in order for this thing to produce torque, since it only has just this one winding, then there has to be a position dependency in the inductance. And does anybody see where that position dependency might be? If you observe this rotor, I'm going to give you the answer kind of, but this is not a round rotor. It's kind of a football-shaped rotor. So where's the dependency of inductance coming from? As this thing moves, the short part of the gap is changing, right? So it might move to a different position over here, and the short gap might be there. You can imagine this thing like lining up over here, right? So the gap length is moving, and you remember that reluctance is equal to the gap, we'll call it G, mu naught over the area of the gap. And so the permeance would be mu naught area of the gap divided by G. And what we can do is we can actually describe fundamental, I'd say the average dominant shape of the inductance position as sinusoidally changing. So essentially what we're saying is that L is going to be equal to N squared times some P constant, and we could call it a cosine or a sine, and there's a variation with theta. Now how many times do you think, just looking at this thing, over 360 degrees, I'm going to see a maximum permeance and a minimum permeance? If you imagine the small gap, there's actually two gaps here. This small passing by I really made a mess of my picture here, but passing by a specific point on the stator, for example, being observed it's going to see a small gap and a big gap and a small gap. How many times do you think it's going to see a variation there? Once or twice?
We'll see it twice.
Right, 2 times. There's going to be, it's really going to look, if you think of it as a sinusoidal variation, it's going to look like that. This is if it was a sine, so if it's a cosine, this is 180 degrees movement, and then this is the next 180 degree movement here. So it's going to go 2 times, so there's a 2 theta. The other thing is that there's going to be some average, in fact, I'm going to use the wrong term here. I'm going to call this P2, but there's going to be some average permeance. It's because the gap doesn't completely close. I mean, the machine wouldn't move, right? It would just rub. So there has to be some averaged, effectively constant inductance here. And so that's what this is times the n squared. So what I have is I have a inductance that is equal to some L naught that's associated to this P naught plus some L2 associated to this P2 here, cosine 2 theta. And I've got a current I that I'm evaluating. Now since I have L and I have I, which of these expressions am I going to use to find the torque? Number 1, number 2, number 3. Right, you're going to use the third one. So you're going to take the derivative of that with respect to theta. So the torque, quite simply, is going to be equal to I squared over 2 times the derivative with respect to theta of L naught plus L2 cosine 2 theta. And then this ends up being equal to minus, now here's an interesting thing. There's some kind of symmetry that's going to show up as we look at these, and like Mustafa was asking about the negative sign and all that, well, in the sign, well, we have it. Now it's because we chose cosine, and it's from this point forward, I'm going to be using cosines when I describe the physical movement of things, and I'll always end up with a sine. I could use sine, and then I would end up with cosine terms here, but it would be mathematically correct. But as we start to think about variations in the current and position, which is what we'll see with AC machines, we'll find out that if you use sines, everything's going to whether you use sine or cosine, you're going to end up with the same basic form. So it's essentially going to be equal to the derivative of this is, we have a negative because the derivative of a cosine is a negative sine. So it's negative, the derivative of this is 0, right? So all you have left is that, the moving part. So 2 times sine 2 theta, and the negative because that's the derivative of a cosine. It looks a lot like this expression here, doesn't it? I'm not going to try to go too much further on that, analogy here, but there is a kind of a symmetry in everything here that there's a lot of complexity to really understand, to get back to this kind of relationship here, but I just kind of have to take my word for it that you can get back to that kind of expression. Anyway, this is the final answer for the torque. So it's quite simple, right? And I gave you a couple of examples. So,
So how come the torque is not dependent on the radius?
because we built it into the permeance variables. So we could have gone in and done some geometrical stuff, and we would have come up with, we could pull that out. It's in here. It's buried in here. It's inside here. Because the area of the gap is this. Here's the gap that you're talking about. So notice that I had the flux crossing the gap. Let me just take half of the gap. Okay, so I mean, I've taken a snapshot of just a portion of this thing. Trying to make sure that it's not the same length. So there's your rotor. And there's your stator back iron. The flux is crossing the gap here. It's crossing this gap. So the area of the gap, it's just like when we talked about this example here, where we had this thing moving in this direction, and we had a gap, and we have a gap here, right? The gap area is this. This is for I'm just showing a piece of a linear kind of rectangular shaped core. This is core. This is core. That's core. So what's the area? The area of the gap, the cross-sectional area is in the middle, right? So if you took a distance r out to that point, the average middle of that point, which corresponds to this, is a function of r. Does that answer that question for you?
Yeah, I got it. So somehow it's hidden in the eye also at the final form.
Not the eye. It's not in here. It's in the. Oh yeah. Yes, it is. I would agree because we've. Well, no, it's. Oh no, hold on. We left out L2. Darn it. It's hidden in here. I wrote this wrong. It's sine. It's minus 2 L2 sine of 2 theta. It's not in the I. It's in the L2. So there's going to be a difference between there's a big gap and a little gap. There's really multiple radiuses here. You know, you've got a radius coming out to the wider part of the gap. Anyway, I'm kind of belaboring this maybe too much. I've got a radius here, R1. I've got a radius here, R2. I've got a radius out to there. You can call it R3. So essentially, you've got a radius out to the middle. That got R0. And so really, the difference between R1 and R2 is what goes into L2. So if you didn't have a varying R, you would not have a torque. And I think that's a point I'm trying to make there. So the average middle of the air gap is associated with the P naught. The variation of radiuses, because we have a difference in the shape of this rotor, is related to the P2. And so these guys are related, and these guys are related. Does that make sense?
Yeah, much better right now.
Okay, good. I got, okay. Yeah, and Adam pointed out the L2 is missing. Thank you. Appreciate it. Okay, so let's go on to multiply excited machines. You guys got to be careful about asking me questions that I really get turned on about, and that's one of them that Mustafa was just asking. Okay, so anyway, multiply excited machines. Can you have machines that are excited by more than one winding? That's what it means. Yes, you can. And so I'm gonna go over this relatively quickly, but because we're going to be working with multiple windings from this point forward, but I just want to show you the top level understanding. So going back to our physics-based approach, where this is, a energy storage system, and magnetic energy storage. Same thing down here. If it was a motor, we could put in flux from one winding right here. We could call that winding 1. It's got a flux linkage, lambda 1, and we've got a flux linkage, lambda 2, and then they have an associated current, I1 and I2. We can get out of that either a torque or a force, right? I'm not going to talk much about force right now, just torque. We can get out of it an angular position or a linearly moving position of x, either way. And then if it was a generator, let's just say that we've got a rotation generator. I could put in a torque and I have a theta rotation. And I've got these, I can get out winding power, a voltage so flux linkage is really, if you take the derivative of that, that's a voltage, right? And a current. So I can get I can get an energy associated with lambda 1 and I1, and I can have additional energy associated with lambda 2 and I2. Now, how you look at these machines, and I want to just think about rotating machines right now, is in terms of this expression here, this matrix. This has just got 2 windings. Note, you could have 3 windings. You could have 4 windings. You could have 5 maybe if you want. I mean, you can have as many windings as you want. I'm just going to write 3 of them down here that are the most common. 3, 4, and 6. Or you can have 2. And why I say common, this is a DC machine. This is a synchronous machine. And this is an induction machine. Or called an asynchronous machine. So we're going to go through these 3 machines for the rest of the class. So you can have more than 2 windings, but I don't want to overwhelm everybody by the math. But essentially, what this says is that the winding 1 is a function of the 2 currents. So if you were to multiply out this matrix, for example, lambda 1 is L11, that's a self-inductance. Now these inductances, each of them may or may not have a position dependency. But if none of them have a position dependency, then you don't have a motor or a generator. You can't produce torque, or you can't put torque in and get electrical energy out. So it has to, at least one of these windings has to have a position dependency. So I've got, this is times I1, I'm just multiplying out this just to show you, and this is L12 theta I2. And then lambda 2 is L21 theta I1 plus L22 theta I2. So your cell, you have your, I don't know, all these doggone colors are going to confuse people. You got your self-inductance, right? And you've got your mutual inductance. So how do you find, you can find expressions. We could go through a whole class period, but it's really not worth the effort right now. And we can derive energy expression. Now the energy, if you're interested, we're not going to have to use this expression because it's just too complicated. But if you want to find energy, you actually have, remember when we derive the energy, our state variables were the flux linkages. We would have to show currents in terms of flux linkages. So you'd have to do this matrix inversion, and you'd have to come up with these expressions right here for I1 and I2 if you want to come up with a co-energy that is related to lambda and L. So, recall, again, going back, what was the single winding? Very simply, the energy, which is a function of lambda and theta, was equal to lambda squared over 2L theta. Just adding one more winding got us to this horrifically ugly equation right here. That's what the energy is. And you have to do an inversion. This D is your determinant for a 2x2 matrix inversion. So it's not easy to find energy from a two-winding machine. But co-energy, on the other hand, and we could have gone through and derived this quite simply, in the same way we did where we looked at, we would have, say, call this theta, we could call this I1, we could call this I2, and we say, here's my co-energy right here. It's a function of I1, I2, theta, and basically derive these expressions, right, by integrating paths along these axes. And the result is we get this expression for co-energy. So remember, the co-energy was 1/2 Li squared, or it would be, the L has to have this position dependency in order for there to be any torque. And really that's what we're after here, There is energy if you don't have position, but there won't be any torque. It's just stored static energy. So L is a function of theta, quite simply, right? Now it becomes this. So we end up having a co-energy in terms of the self-inductance term right here, L11, L22, and then the mutual inductance, L12. And now we could simply find the torque in three different ways, just like we did before. Partial derivative of the expression of the energy evaluated at a specific flux points, the partial derivative of co-energy evaluated at specific currents, or this expression here. Okay? Now we're right at the last piece of this here. I get kind of upset with myself, but So anyway, I'm just going to take a few minutes, if it's okay here, talk about this multiply excited machine, and then we'll be completely set up to talk about the chapter 4. And here's a machine with two windings. I have a winding on the rotor right here, and I have a winding on the stator. So the stator, looks like our typical magnetic core. And then I've got this rotor moving here. Now this particular example is just going to move you in a direction, but notice it's connected to a spring. So it's not going to be moving all the way around. It's not going to be doing this kind of thing continuously. It's just going to go move this way, move that way. It's kind of moving two ways. So it's really kind of an actuator. You could say, okay, I could wind my windings really loosely on this machine and it'll just pick up the slack and it's okay. But the trick is how you get the current onto the rotor, and we're going to talk about that in the next lecture. But anyway, I've got two windings, and so lambda 1 is on the stator right here, and lambda 2, winding 2, is on the rotor. And you could go through a lot of kind of chapter 2 type of analyses and come up with inductance and expressions for this. But this problem gives you those. And this is typically, I'm not going to make you guys do geometric, except for that one homework problem. This isn't really a geometry class, okay? But I'm going to write the final expression. L11 is the self-inductance is 3 plus cosine 2 theta, and there is, if it were to go all the way around, if you're going to move all the way around 360 degrees, you would get a 2 theta variation in inductance. So we do need to put this term in there, even though we're only moving part of the way. It's still based on 360 degree rotation. And then this would be times 10 to the negative 3. This is actually henries, right? That's the same as saying 3 plus 1 cosine 2 theta millihenries. And it's kind of saying, okay, I got an L naught of the 1 that is 3 millihenries, and I have an L2 of the 1 that is 1 millihenry. That's another way to think about this. And then I've got an L12 mutual, which is the mutual inductance between these two windings here, 0.3 cosine of theta. Now here's an interesting thing, and it'll become clearer, and this is again millihenry. We actually have an example here of two windings, and we can call this winding here a field winding. We can call this winding here an armature winding. And this is actually what I would call a synchronous machine. And it will have to have AC currents. I'm sorry, let me just not get too ahead of myself. This will be AC here. So the current either supplied, or if it was a generator, if you were moving this thing and trying to produce a voltage, the current here would be alternating current. But here you would want to supply a DC current. So it's kind of like a magnet. And so essentially the field is like a magnet that you're moving. And the armature is getting an AC current in it as a result of the movement. And that's really what the difference is between these two types of windings. So this is kind of saying, okay, what I really have is I've got a mutual inductance, I'll call it L sub M, equal to 0.3 millihenries. It's really due to this DC rotating field, and it's only got a position. There's no static inductance there. That's very common. And then the final inductance is L22. In this case, it's such a weird structure, but it's 30 plus 10 cosine 2 theta, probably because the winding on the field has a lot of turns, which is typically true of field windings. And you have typically less turns on your armature winding there. And so it's 30 plus 10 cosine 2 theta millihenries, is saying that you've got a static self-inductance of 30 millihenries and a varying self-inductance of 10 millihenries peak. So now since you've got these three inductances, you simply go back to this expression right here. And you're going to say, okay, let's plug them in. So I've got to take a derivative of L11, of L22, and of L12. And that's really how you solve this problem. And this is really the kinds of problems I would be having you do in homework or exams here. So the torque expression here ends up being, since you were given inductance and you're given the current, both of the currents, you got I1 squared over 2, and the derivative of this, okay, so that ends up being, for example, minus 2 times 10 to the negative 3 sine of 2 theta plus I2 squared over 2. I don't mean to make it look like this is a absolute value. The derivative of the self-inductance of the other winding, that's going to be minus 20 sine of 2 theta. And then you're going to add the product of the two currents times the derivative of the mutual inductance. And that ends up being 0.3. Oh, notice here, this isn't a millihenry. I screwed up on this. I'm looking at this is actually example, I think 3.7 in the textbook. 0.3, so it's 0.3 henries. Usually your mutual inductance is a really big number, so that'd be the same as saying 300 millihenries. 0.3 times the, again, sine of theta. And there's no 2 variation on this one.